Okay, so let's start this last lecture on the content. And we're going to talk about the discontinuity enriched finite element method that we baptize as the DE-FEM. And the idea was basically to extend the IGFEM that we looked at in the one of the last lectures. As you know, IGFEM was able only to deal with weak discontinuities. So that what we did for this work is extend the formulation so that we could actually solve problems with the strong discontinuities. So we moved from material interfaces to fracture mechanics, to cracks. You know, the types of problems that can be solved with XFEM enrichment functions. Okay. So this is our model problem here. We have a bar as usual, and the bar is composed with the same material throughout. So you see that EA is constant throughout the bar, but at some location gamma C, we're splitting that bar into two components, and we're reattaching that with a spring, and the spring has constant K gamma. Okay, that is the idea. So intuitively, you can basically understand that for this problem, the maximum displacement, or the displacement at the right end of the bar, is going to be composed by the deformation of the bar plus the deformation in the spring. Yeah. So who remembers what is the deformation given to the displacement due to the deformation of the bar? Someone remembers that? P times L divided by, no one?
Divided by EA.
Yes. PL divided by EA is the deformation of the bar plus, and the deformation in the spring, simpler.
P over K.
P over K. Very good. Yeah. So that would be the total deformation that you have at the right tip. Now, what we want to do here is exactly the same thing that we did for the IGFEM. So we want to solve this problem with one finite element. And we want to add an enrichment to that formulation, right? To be able to obtain the exact solution, which is, again, PL divided by EA plus P divided by K, K gamma in this case. Okay? So that's what we want. So if I have one finite element, my partition of unity, how many functions I have? Two. And these are shown here. Okay, so the exact solution for that problem, I'm showing that here. And you see that, of course, the solution is linear. And at some point, there is a jump. That is a strong discontinuity. There's a jump in the displacement field. And then if you notice, the slope of that curve does not change. And the reason for that, and we're going to talk a little bit about this later, is because the materials properties of the bars are the same at either side of the bar. In general, this doesn't have to be the case. You could have different material properties at each side of a discontinuity. But for this particular example, we're going to look at having the same material properties at either side. So what we're going to look is a solution similar to that of IGFEM, where my approximation is going to be composed by the partition of unity shape functions, which in this case I have two, as we said. And then we're going to add an enrichment, right? In this case, if you remember the terminology for IGFEM, my alpha degree of freedom, the generalized degree of freedom alpha, was associated with the enrichment functions. So for this particular case, for the strong discontinuity, I call my enriched degree of freedom beta. Okay, so this is my enriched DOF, and this T is my enrichment function. And of course, this is standard FEM, as we already know, and the second term is the enrichment. Yeah. Now we're going to think a little bit how we can construct that G function. So if I want to introduce a strong discontinuity, so there's going to be a jump in the displacement field, then I have to use an enrichment function that exhibits that jump, okay? And we're going to follow the same procedure we did for IGFEM. We're going to construct that enrichment function using as a helper the Lagrange shape functions in integration elements. So if you remember, what we did is, well, we are subdividing the bar into two components, right? And then what I'm going to do is to use the Lagrange shape functions of those two components to build my enrichment function. Okay? Okay. So how does it look like? G then is going to be equal to, and I'm going to explain what I do in a minute, gamma C due to 1, and then 1 minus W. Okay. So I call this W the location of the discontinuity relative to the length. So W for this case is gamma C divided by L. And what I'm doing here, if you see, is I'm taking basically this first function and I'm flipping it. So I'm basically multiplying that by -1. Okay? And then for the other side, I'm taking this function and the sign remains the same. So it turns out that by using this choice, right, what I ensure is that the jump is exactly 1 at the location of the discontinuity. So if you do the math, so here is basically minus gamma C divided by L, and then that shape function, which is phi gamma C of integration element 1, can be written as x divided by gamma C. So the first shape function is equal to minus x over L. And this is for x less than gamma C, which, if you think about it, is the shape function of the partition of unity. So I basically took, I constructed this first part of the function, and I end up with x over L, and x over L is this function here. Yeah, but I'm just inverting that. For the second one, if we do the math, you have 1 minus gamma C divided by L, and then the other shape function for that discontinuity for the integration element can be written as L minus x, and then L minus gamma C, which is equal to 1 minus x over L for x greater than gamma C. And if you think about that equation, is basically that curve. So it's very interesting because we have built our enrichment function using integration elements, but by multiplying those functions by minus w and 1 minus w, what we get is an enrichment function that is basically using the partition of unity of the parent element. You see that? It's just that one is inverted. So if we look at the left of the discontinuity, I have this function inverted. So it's going to look something like this, right? And if I look at the right of the discontinuity, then I have this function. So it's a very interesting choice that gives me the jump is equal to 1 and exactly equal to 1. And this has a tremendous advantage. Who can tell me what that is? If the jump, if this guy here at the discontinuity is equal to 1, what is beta?
Beta should be the magnitude of the discontinuity.
Yes, and that is great. So physically, beta has this meaning of being the jump at the location of the discontinuity. Yeah? And this is good. So if we plot the enrichment function, then the enrichment function is going to look something like this. Yeah? Where this is equal to 1. So at this side of the discontinuity, I have minus W phi gamma C of integration element 1. And on this side, I have 1 minus W and then phi gamma C of integration 2, which leads to those two equations, minus x over L and 1 minus x over L, right, to produce that jump. So this function is a very nice function, because as with IGFEM, what is the value of the nodes of the element? 0. And this has great implications. Who can tell me why it's nice to have that 0? Why is it nice that the value of this enrichment function at this location is equal to 0? Because applying boundary condition is as straightforward as in standard FEM. We don't need to do a special tricks. So we basically obtain the same advantages that we discussed with GFEM, but now for strong discontinuities. Okay? So now that we have our enrichment function, let's see how integration of the stiffness matrix and the force vector takes place, and then we build our system, and then we're going to solve it, and you'll see that we recover the exact solution. So okay, for this case, again, we are splitting into two because we always want to integrate smooth functions, so we need to separate, right? We need to integrate in parts, right? So we divide that bar in integration elements, and then our stiffness matrix is going to be written like this. So you have dn dx transpose dn dx, and then there is going to be the second term that is very similar to this. Only that we are integrating from gamma c to L, and I'm missing the dx here. Okay, and as in GFEM, what we do, the only difference that we do from GFEM is to stack together the partition of unity shape functions, and we put at the back, we put the enrichments. The same thing we discussed many times. Although there is a subtlety, and we discussed this last class, when it comes to the implementation, you have to deal with these two Jacobians as we discussed, okay? That is the only trick. But for this particular problem, for this very simplified problem, we're not going to do any transformations, so there are no Jacobians involved, right? So if you take, in this case, n is going to be a vector where I'm stacking together the partition of unity shake functions, and I have my enrichment. Yeah. Now, there is also the constant, that spraying that is joining these two bars, that is basically connecting this whole thing together, right? Otherwise, I cannot solve this problem. If I do not connect the first component of that bar to the second one, and then I basically apply a force to the right-hand side, right? The system will be singular. So somehow I have to connect these two components, and that is happening through the spring at the discontinuity. Okay, so we're gonna define an array M, just 0, 0, 1, to make that connection possible. So the derivative, which we need to build the stiffness matrix, then is going to be equal to minus 1 over L, 1 over L, and minus 1 over L. And this is for x less than x gamma. In this case, x gamma is my gamma c. And then similarly to the right, this is going to remain the same because the partition of unity doesn't change inside the element. And this is also going to be the same, right? Because the derivative of that function, if you see, is the same. So the slope of this enrichment function is exactly the same. And this is for x greater than gamma c. And I will explain later why we're not doing only one integral here, okay? So if we do this, when our K matrix is going to be equal to the integral, and then we just have to do this computation, so minus 1 over L, 1 over L, minus 1 over L. Dx plus, I forgot to add here the contribution of the spring, which is K gamma, just M transposed M. So I have that contribution, and I have this contribution here. Yeah, and I have finally one term that is multiplying a matrix that is basically connecting that degree of freedom corresponding to beta, okay? And this, if you do the math, this is basically EA over L, and it has a very similar structure to what you would get if you're not using any enriched formulation. So the standard component is exactly the same as the standard FEM part. So you have EA over L, 1 minus 1 minus 1, 1. And then you have the coupling terms that appear because you are using or you are enriching the approximation. And in the last term here, you have basically that coupling term given by the spring divided by EA. And this is your stiffness matrix. It's just simply carrying out all this math, but you get that stiffness matrix, okay? And if you see, it was very simple because the only thing we need to do is to add the enrichment at the back of our array that contains the enrichment functions and shape functions, and we just define this matrix M to provide the coupling given by the spring at the location of the discontinuity. So this is the stiffness matrix you get. Now the force vector should be very straightforward for everybody. So who can tell me what the force vector is?
I have a question.
Yeah.
The x is not L, so I'm missing a length measure or so.
The x is not L?
Yeah.
Well, you're integrating x, right? So you have an integral between...
Oh, excuse me, yeah, right.
Okay. It's okay. So who can tell me what the force vector is? Yeah.
R0P.
Sorry?
R0P.
Think about it again. The first degree of freedom is a left end.
Oh, I'm sorry.
So it's R,
RP and then
R, P,
something.
and
Something
0.
Yeah.
Right? So let's solve the system. Very simple, right? We have this leads to our system K U equals F. So we have, let's copy this guy here. And then we're going to have our degree of freedom vector, which is what? Who can tell me?
U1, U2, and beta.
U1, U2, and beta. Very well. This is equal to R, P, and 0.
What does R mean here?
The reaction force. Yeah. So as usual, we proceed as usual, as we have seen already many times. We cross this row, we cross this column, we assign a value of 1 in the diagonal, and then the value of 0 to the right hand side. So we basically transform our system to remove the singularity given by the rigid body mode. And well, if you solve this problem, you get the solution vector. What you get is U is equal to 0, as you would expect, and then you have PL divided by EA plus P divided by K gamma, and then the enriched degree of freedom is P divided by K gamma, which is what we discussed in the beginning of this example, right? The displacement at the right end is basically determined by the elongation of the bar plus the elongation of the spring. Yeah, and what is very nice is that the enriched degree of freedom immediately tells us what is the value of the jump, right? Because of this property of the enrichment functions that we built, that the jump at the location of the discontinuity is exactly equal to 1. So in a way, we are harnessing the partition of unity, right? So if we take the two shade functions of the partition of unity, and basically we flip one of them, right? Anywhere along the bar, 1 minus the negative of the other one is going to be equal to 1. And that is what we use to construct the enrichment. Okay. So let's add a note here. So this is the deformation of bar. Plus deformation of the spring. And this is the jump. Okay, so we were able to get the exact solution for that problem.
Excuse me.
1 second. And we got to the solution of this problem very simply because we consider the same material properties at each side of the bar, right? So that means that there is really no jump in the strain here. And this is very important because if you just change the material properties at either side, so if I have, for example, EA on the left, it is not equal to EA on the right, we are unable to get two independent kinematic fields with this formulation, right? So we noticed this when we submitted the paper, and then basically the solution to that was to just use the standard IGFEM formulation, which has that term, right, with the alpha enriched degree of freedom, that is reproducing that jump in the gradient, and then we added the strong term into it, right? So in other words, right now we are solving this problem with 3 degrees of freedom, right? But if I really want two independent fields to the left and to the side of the bar, 3 degrees of freedom is not enough. I need 4, right? So if you were to solve this with the standard FEM, you need 2 degrees of freedom to represent the displacement on the left component and 2 degrees of freedom on the right. You follow me? And now the formulation that I'm using has only 3. So kinematically, it is not possible to recover the general solution for which the slope changes at either side of the bar. You have a question?
Yeah, excuse me, what is the first sign in the last vector?
Sorry?
Looks like a 0, but is it?
It is a 0.
Oh.
It is your displacement at the left hand. Okay, so let's write that note. Okay, so in general, the material properties don't have to be the same. So E1, A1 is not equal to E2, A2. Fails to produce two independent fields. And so the solution for that, as I said, was basically using the IGFEM formulation right? And then add the strong discontinuity term into it. So now if you see my DE-FEM formulation, general DE-FEM formulation has 2 enriched terms. This one is taking care of the weak discontinuities, and this one here is taking care of the strong discontinuities. And this is great because if you're solving a problem and you basically don't have a strong discontinuity, your formulation falls back to the IGFEM formulation.
Can you repeat what the difference is between strong and weak?
Yeah, so a weak discontinuity is a discontinuity in the gradient, right? So it's a C0 field. So then if you take the derivative, there's a jump in the gradient. And a strong discontinuity is a jump in the field itself.
So GFEM isn't able to deal with strong discontinuity.
IGFEM. So IGFEM was devised only for weak discontinuities, right? Because the enrichment functions basically are Z0 continuous, they have a kink, right? And so for the strong discontinuity, we added this additional term that is taking care of the jump in the field. Okay? So that would be the final, let's say, formulation for 1D. If you extend this to 2 dimensions or to 3 dimensions, so let's put in higher dimensions. Then we have UH, which is now a vector. That is a function of a vector position. Sum phi of x multiplied by ui plus, there is a sum here that is taking care of the weak discontinuities, and there is one last term that is taking care of the strong discontinuities, and these are also vector. Okay, so that's it. So this is basically a very simple explanation of what DE-FEM is. And the good thing is that it retains all the nice properties of GFEM. So we're going to summarize to finish this quick lecture on DE-FEM. We're going to summarize the advantages again. And I put GFEM / XFEM because, as you guys know already, they are the same. Okay, so what are the advantages? Again, the degrees of freedom are added where? To the discontinuity. To nodes created along the cracks, instead to those of the original mesh. So the enrichment functions were constructed in a way that they were local, right? So they are completely zero, exactly zero outside the representative elements, which also is nice because we don't have issues with blending elements anymore, okay? Thus, there are no issues with blending elements. Okay, another thing, we actually use those integration elements to construct the enrichment functions. So remember that in GFEM, we need to split in integration elements anyways for integration purposes because we want to integrate smooth functions. But in this method and in GFEM, we actually take advantage of those integration elements to construct the enrichment. Which need to be created anyways for quadrature. Another important advantage, the same as in GFEM, is that these functions are exactly zero at the mesh nodes. So these mesh nodes then retain the Kronecker delta property, and that means that standard DOFs retain their physical meaning. And this is not the case in GFEM. or you have to do some tricks, right? The shifting, we talked about it. Now, this fact that enrichment functions are exactly zero, we already said that has benefits in terms of prescribing boundary conditions. Yeah. And there was one more advantage of a GFEM. We look at the stability, and we said that if you do things the right way, the method is stable. So as you refine your mesh, your condition number of the stiffness matrix doesn't blow up as the discontinuities approach the mesh nodes, right? And the same happens here in DE-FEM. And we actually have an article that was accepted last week in DE-FEM in 3D where we show that the method is stable. So the condition number of the stiffness matrix grows at the same rate. As that of standard FEM. Who remembers what was the rate? Order of h minus 2. Okay? So these are the advantages of the method. So this is something very new. We published this method in 2017, and since then, of course, we have been working very hard, and we have been extending this formulation to tackle all sorts of nice and different problems. So still there is a lot of work to be done. So there are any questions? No questions? Okay, so let's take a quick break before we delve into those slides that I talked to you about, okay?